All right, so in this video, we're going to be talking about the equilibrium of rigid bodies. All right, so pretty much what that means is you're going to be finding your reactions. Like on a beam and stuff. So what it means for a rigid body to be in equilibrium is that all of the forces in every direction, so the sum of forces x, sum of forces y, and the sum of moments about any given point are going to add up to equal 0. All right, so if you have forces going up and forces going down, in order for that object to be in equilibrium, these forces have to cancel each other out so their sums equal 0. Otherwise, your beam would be moving and it would no longer be statics, it would be dynamics. So first, let's go ahead and just look at different types of reactions that you might see on a beam. There's a pin, a roller, and a fixed connection. All right, so these are the three most common types of restraints that you will see as pertaining to beams. Now, when you're looking at these, you want to look at the different directions in which the beam would be restrained from movement. So as you see this pin here, if you tried to pull on your beam in this way, it's not going to move. So therefore you would have a reaction force in the x direction. Now if you try to pull this pin up like this, it's going to hold that beam down. So you're also going to have a reaction in the y direction. Now, if you pushed out here on the beam, it would be allowed to rotate this way, so we won't have a moment reaction there at that pin. All right, so when you're trying to determine what your reactions are, you kind of need to ask yourself in what directions is movement restrained. All right, so in what directions can the beam not move? It can't move in what directions? So for your pin, it can't move in the x and y directions. So we would have as I said before, a reaction in the y and a reaction in the x. Now for a roller, if you were to push on this, it would just roll and continue to roll that way. So we're not going to have a reaction in the x, but it can't move in the y, so we'll have a reaction in the y. Now for a fixed beam, we can't move in the y, we can't move in the x, and we also can't move in rotation, so we will also have this reaction moment out there on the end. So let's look at a couple examples of these just really quickly. Really simple examples. If we have a simply supported beam, and all that means is that you're pinned on one end and you have a roller on the other. That's what simply supported means. We've got a point load in the middle here. We'll say it's 5 feet on either side of that point load, and the point load is 10 kips. And we want to find our reactions. The first thing you're going to do is draw a free body diagram. And now this is a diagram of the beam that puts all the forces, all the external forces that are acting on the beam. So we've got our 10 kip point load, that's acting on it. And then we also have our reactions that are acting on this beam. So we've got our reaction in the y and reaction in the x, and then another reaction in the y over here. We'll label this side A and this side B. So we're going to have a reaction AY, AX, and BY. All right, and then you can just start summing forces. So I always like to start with sum of moments. And I just do it about the far left point on that beam. You can do it on any point of the beam, and it will work out. Equals 0. And then I'm going to pick a direction to be positive. You can pick either direction. It's fine. You'll end up with the same answer. So sum of moments about A equals 0, and I'm going to choose clockwise as being positive. So I'm taking my moment about this point here. And so you're going to take every force and multiply it by its moment arm. Now for AX and AY, their moment arm is 0, so they don't cause any moment about point A. So we'll start with this 10 kip force there, and its moment arm is the perpendicular distance over to the point you're taking your moment about. So that's going to be 5 feet. And that's positive because as we push down here, the beam wants to rotate this direction around point A, which is we defined as the positive direction. So then we've got BY and its moment arm of 10 feet. And that would cause a negative moment, so we'll minus that. That's all of our moments, so we can set that equal to 0 and then solve for our unknown. So if you solve for BY, you'll get that it equals 5 kips. Now we ended with a positive 5 kips, so our assumed direction that we drew up here is correct. So it'll be 5 kips pushing up. All right, now if we do our sum of forces, X equals 0, choose going to the right as being positive. We've got AX and nothing else, so AX equals 0. And then we'll do our sum of forces, Y equals 0, choose up as positive. And so just going left to right, we've got AY positive minus 10 kips plus BY equals 0. So AY minus 10 kips plus 5 kips equals 0. So we solve for AY and we'll get that it equals 5 kips. And again, that's positive, so the direction we assumed right here is correct. So that'll be 5 kips going up. All right. So that would be for a simply supported beam. If we look at an example of a fixed beam, we'll just stick a 10 kip point load out on the end, and this beam is 10 feet long. So again, I always like to start with my sum of moments. About A equals 0, choose a positive direction. Again, draw your free body diagram. So our reactions over here are going to be reaction Y, reaction in X, and we will also have a resultant moment because it's fixed. So about A and Y have 0 moment arms, so we're just not going to include those. But we've got our resultant force MA, and we drew that in the positive direction, so we'll keep that positive. And then we've got 10 kips times its moment arm of 10 feet. And that would also create a positive moment. So that'll be positive there, and that would be all of our forces that create moments. So we're going to set that equal to 0. Solve for our unknown, and we get MA equals negative 100 kip feet. Now, because this is negative here, we assumed this direction wrong. We drew that arrow incorrectly to begin with. So we will just rewrite MA equals 100 kip feet positive, and then rewrite this arrow as going that direction. And that would be our answer. All right, then you do your sum of forces. X equals 0, assume a positive direction. And we've got AX, that's our only X direction force, so that equals 0. And then sum of forces, Y equals 0. So we'd get AY minus 10 kips equals 0. So AY equals 10 kips. Positive, so we assume the direction correctly. So it would be going up. And that would be your answer. So let's go ahead now and let you try some on your own. All right, so the first one is a simply supported beam. And you've got a rectangular distributed load acting on it. Magnitude of 5 kips per foot and a length of the beam of 10 feet. And for number 2, you'll have a fixed beam with a point load of 5 kips on the end and a concentrated moment of 30 kip feet acting at the center where this beam is 5 feet to the center and 5 feet on the other side, so 10 feet total. And again, for both of these, go ahead and find the reactions to provide equilibrium to the rigid body. All right, so you can go ahead and work those out, and then you can check your answers with the solution in the PDF found below this video. And that's all we have to cover for equilibrium of rigid bodies. So go ahead, work these out on your own, check your answer, and then go ahead and do the quiz.